A line is said to be parallel to a projection plane when it never meets that plane, no matter how far it is extended. Imagine a rail track that runs alongside a wall without ever touching it. The track is parallel to the wall. In engineering graphics, we classify such lines into two useful groups. True-length lines, the line's direction is exactly parallel to the projection plane. Therefore, its length appears unchanged, true, in the view that is projected onto that plane. For example, a horizontal rod lying on a table will show its actual length in the top plan view because the rod is parallel to the table, the projection plane. True-shape lines, the line may be inclined to the plane, but still lies in a plane that is itself parallel to the projection plane. In this case, the shape, the angle it makes with other lines, is preserved, although the length may be foreshortened. Projection systems describe where the object is placed relative to the imaginary picture planes. First angle projection, used mainly in Europe, imagines the object in the first quadrant, that is, the object is placed between the observer and the picture plane. When a line is parallel to a plane, the view of that line is drawn on the same picture plane that it is parallel to, and the other views are placed on the opposite side of that plane. Third angle projection, standard in the United States, imagines the picture plane between the observer and the object. Here the view of a line parallel to a plane is still drawn on its own plane, but the arrangement of the remaining views is opposite to first angle. Understanding this classification helps you decide which view will give you the true length of the line. When a line is parallel to a projection plane, its orthographic projection onto that plane gives us two important pieces of information. True length, because the line never meets the plane, the direction of the line is exactly the same as the direction of the projection rays. Therefore, the distance measured on the drawing is the real distance in space. Think of shining a flashlight directly sideways onto a wall. A stick that runs parallel to the wall casts a shadow of exactly its own length. True shape, if the line lies in a plane that is itself parallel to the projection plane, the angles that the line makes with other lines that are also in that plane stay the same in the view. For example, a ladder leaning against a vertical wall, both ladder and wall are parallel to the floor. The ladder's inclination angle to the wall looks the same in the floor plan view as it does in reality. To determine whether a line will appear at true length, check the line's direction vector d against the normal vector n of the projection plane. If d.n equals 0, the line is parallel and the projection will be true length. If the line is not exactly parallel but lies in a plane that is, the shape angles will still be true, but the length will be foreshortened by the cosine of the angle between the line and the plane. Step-by-step construction in the first angle system. Identify the projection plane, for example front plane, top plane, or side plane, to which the line is parallel. Draw the three principal projection planes in their first angle arrangement. Front plane in the center, top plane placed below it, and side plane placed to the right of the front plane. Locate the line on the object and note its endpoints A and B in 3D space. Since the line is parallel to, say, the front plane, its direction vector d satisfies d.n front equals 0. Project each endpoint onto the front plane. Drop a perpendicular from it to the front plane. The foot of this perpendicular is a prime. Do the same for B obtaining B prime. Because the line is parallel, the perpendiculars are parallel to the projection rays and have equal length, so a prime B prime on the front view is the true length. Transfer the projected points to the other two views using auxiliary lines. From a prime, draw a line parallel to the top plane normal, which is the vertical direction to intersect the top plane. Label the intersection a sub t. Do the same for B prime to get B sub t. From a prime, draw a line parallel to the side plane normal, the horizontal direction, to intersect the side plane. Label these points a sub s and B sub s. Connect the points in each view. A prime B prime on the front view represents the true length. A sub t B sub t on the top view represents the true shape and may be foreshortened. A sub s B sub s on the side view represents the true shape. Check the construction. Verify that the distances a prime B prime, a sub t B sub t, and a sub s B sub s satisfy the relationship the magnitude of a prime B prime equals the magnitude of a B, and that the projected angles in the top and side views match those measured on the object. Step-by-step construction in the third angle system. Set up the three principal planes in the third angle layout. Front plane in the center, top plane above it, and side plane to the left of the front plane. Identify the plane, for example the front plane, that the line is parallel to. Mark the real endpoints A and B of the line in space. Because the line is parallel to the front plane, the direction vector D obeys D dot n front equals 0. Project the endpoints onto the front plane. Draw projection lines perpendicular to the front plane. These are the sight lines. The feet of these perpendiculars give a prime and B prime on the front view. The segment of prime B prime will be the true length of the line. Obtain the top and side projections. From a prime, draw a line parallel to the top plane normal downward direction until it meets the top plane. The intersection is a sub t. Repeat for B prime to be sub t. From a prime, draw a line parallel to the side plane normal rightward direction until it meets the side plane. The intersection is a sub s, likewise B sub s. Connect the points in each view. A prime B prime on the front, true length, a sub t B sub t on the top, a sub s B sub s on the side. In third angle, the top view appears above the front view and the side view appears to the left, which is opposite to the first angle arrangement. Verification. Ensure that the front view length equals the actual length measured on the model and that the projected angles in the top and side views are consistent with those measured on the object. Use a ruler or a CAD check to confirm. Direction cosines. Any line in space can be represented by a unit direction vector D equals L, M, N, where L, M, N are the cosines of the angles that the line makes with the x, y, z axes respectively, and L squared plus M squared plus N squared equals 1. Plane normal. For a projection plane with unit normal N equals a BC, the line is parallel to the plane if the dot product of D and N, that is L plus MB plus NC, equals 0. Projection matrix onto a plane. The orthographic, also called parallel, projection of any point P onto a plane with normal N is given by P subproj equals open parenthesis I minus N transpose close parenthesis P, where I is the 3 by 3 identity matrix. The matrix M equals I minus N transpose, which expands to a 3 by 3 matrix with entries 1 minus a squared, negative a B, negative a C, negative a B, 1 minus B squared, negative BC, negative a C, negative BC, 1 minus C squared. This matrix removes the component of the point that is normal to the plane, leaving only the component lying in the plane. Applying to a line, take the two endpoint vectors A and B, their projections are a prime equals M A and B prime equals M B. The segment from a prime to B prime is the orthographic view. If the dot product D dot N equals 0, the length of a prime B prime equals the length of a B, confirming true length. Example, suppose the front plane is the YZ plane, whose normal is N equals 1, 0, 0. The projection matrix becomes M equals a matrix with first row 0, 0, 0, second row 0, 1, 0, third row 0, 0, 1. Multiplying any point with coordinates x, y, z by M simply discards the x coordinate, leaving 0, y, z, the classic front view. Any line with direction vector 0, L, M, that is, no x component, is parallel to this plane and projects at true length. Using an auxiliary inclined plane to reveal true length. When a line is parallel to a principal projection plane, its true length is already visible in that view. However, if the line is only parallel to a secondary plane, for example, it lies in a plane that is parallel to the front plane, but the line itself is inclined, we can tilt an auxiliary plane so that the line becomes perpendicular to that auxiliary plane. The steps are: select an auxiliary plane that makes an angle theta with the principal plane, such that the line's direction vector becomes orthogonal to the auxiliary plane's normal. In practice, this means the auxiliary plane's normal n aux satisfies D dot n aux equals 0. Rotate the object conceptually so that the auxiliary plane coincides with the drawing paper. The line now appears true length in the auxiliary view because the projection direction is parallel to the line. Project the endpoints onto the auxiliary plane using the standard orthographic method. Draw perpendiculars to the auxiliary plane. The distance between the projected points equals the actual length of the line. Transfer the true length back to the principal views if needed. Measure the length on the auxiliary drawing and copy that dimension onto the front, top, or side view as a true length dimension. Real-world analogy. Think of a ceiling-mounted ruler that is slanted relative to the floor. You cannot read its true length from a floor plan. If you stand a ladder against the ruler and look straight down the ladder, making the ladder the auxiliary plane, the ruler appears end to end, letting you read its exact length. Mathematical check. If the auxiliary plane is defined by normal n aux and the line direction is D, The condition d.n aux equals 0 guarantees that the projection matrix m aux equals I minus n aux times n aux transpose will not change the magnitude of d, hence the norm of a prime b prime equals the norm of a b. Explanation: typical examination problems. True length identification. Given a line drawn in a multi-view set, state which view shows its true length and measure it. Requires recognizing that the line is parallel to that particular projection plane. True shape determination. Provide the angle that a line makes with another line when both lie in a plane parallel to the front plane. Tests knowledge that angles are preserved true shape even if lengths are foreshortened. Construction in first angle. Draw the front, top, and side views of a line that is parallel to the top plane. Checks the ability to follow the first angle layout and to project endpoints correctly. Construction in third angle, same as 3 but using third angle rules. Confirms the student can switch between projection conventions. Auxiliary plane problem. An inclined line is given, choose an auxiliary plane and show the true length view. Evaluates skill in selecting an appropriate auxiliary plane and using projection matrices or geometry. Mathematical verification. Using direction cosines, prove that a given line is parallel to a specified plane. Requires algebraic manipulation of dot products and understanding of cosine relationships. Error checking. A set of multi-view drawings contains one incorrect view. Identify and correct it. Tests the ability to spot common mistakes such as mixing up first-third angle or Mies drawing true-length views. Common mistakes, checks, and precautions. Confusing first angle with third angle. The two systems are mirror images. Students often draw the top view on the wrong side. Keep a cheat sheet that shows the layout of both systems side by side. Before starting, state explicitly which system you are using. Treating any line as true length. Forgetting the dot product test d.n equals 0. For every line, write its direction vector or estimate and the normal of the candidate plane. Compute the dot product quickly, even mentally, to confirm parallelism. Projecting endpoints using the wrong normal direction. Mixing up the direction of projection rays, for example using the normal of the auxiliary plane instead of the principal plane. Draw a small arrow on each plane indicating the projection direction, usually outward from the object. Use that arrow consistently. Incorrect scaling on auxiliary view. Assuming the auxiliary view automatically gives true length without verifying the auxiliary plane is truly perpendicular to the line. After selecting the auxiliary plane, double-check the condition d.n sub aux equals 0. If not, rotate the auxiliary plane until the condition holds. Missing true shape preservation. Measuring lengths instead of angles in a view where only shape is true. Remember the rule, if the line is not parallel to the plane, only angles are true. Measure angles with a protractor or CAD tools, not lengths. Overlooking hidden lines. When a line lies behind another feature, students may omit the hidden line representation. Apply the standard hidden line convention, dashed lines, consistently in all views. Rounding errors in calculations. Using approximate direction cosines leads to small but significant errors in length verification. Keep direction cosine values to at least 4 decimal places. Use a calculator or spreadsheet for dot product checks. Final checklist before submitting a drawing. 1. State the projection system. 2. Identify which view should contain the true length. 3. Verify dot product condition for each line you claim is true length. 4. Ensure auxiliary views are correctly inclined and that the line becomes perpendicular to the auxiliary plane. 5. Review hidden line conventions and label all dimensions.